For that introduction, and thanks everyone for coming to my talk on what is essentially how we can use these really cool class of models to understand why birds and frogs are making noise. So before I get started, I just want to acknowledge all of the funders who've made this work possible, especially the Natural Resources Conservation Academy, Great Hollow, who have made it possible to have high school and undergraduate students working on this project. To start with, I want to talk about, or I guess define what I mean by an acoustic signal. So this includes things like birds singing or primates howling, frogs chorusing or calling, but also non-vocal communications such as using air sacs to make booming noises, or of course vibrational noises like you would get with grasshoppers and crickets. And so all of these are really different types of signals, but they all kind of fill the same general purpose when we're thinking about signaling. For example, we know that animals will use vocal communication, or sorry, I should say acoustic signals to include all of those vibrational and air noises. So we know that animals will use these acoustic signals to, for example, establish territory at the beginning of a breeding season, to defend those territorial boundaries against potential intruders, or even to non-aggressively respond to neighbors to keep maintaining those boundaries without actually needing to actively defend them. Also, one of the classic examples that we think of is attracting a mate, so really common with insects or birds to be just emitting a signal in order to attract a mate. And of course, to warn other individuals about the presence of a threat or predator. And I'm going to focus on the first four of these types of signals because in terms of predators, you really need to know whether or not there is an external threat or predator that an animal would be warning about in order to understand what's going on with that behavior. But the other four, we can kind of broadly group into two general classes. And so I would say that establishing a territory and attracting time of the breeding season, and same thing with attracting a mate. So an orthopteran may be signals to a signal from a neighbor or another individual. And usually when we're going to model any type of acoustic signal, we're going to do this as a Poisson process, because you can think of it as you're just counting up the number of signals or vocalizations that occur over a given period of time. And that helps us be able to understand, how often birds are singing or how often frogs are calling, but that doesn't actually tell us why they're signaling. So we don't know if a signal is because an individual is defending territorial boundaries or attracting a mate, unless they have different signals that they use for these different underlying behavioral motivations. And for many species, that's not the case, and it's the same exact signal no matter what the underlying behavioral motivation is. So when we model this as a Poisson process, that doesn't really tell us what the behavioral motivation is. And so for that, we actually have to turn to the stock market because they have really good models to understand individual behaviors and motivations. For example, we can look at Bitcoin trades over time. And so on the y-axis here, we have the volume of trades, and then the x-axis is time of day. And you can see that there's kind of a cyclical pattern, but the main thing to note is that you have these peaks or spikes in volume of trading, and then it declines. And these spikes can come from a couple different things. So it could be external motivation where there's been some kind of news or event, but it could also just be that individuals are paying attention to what other people are doing in the stock market and following their behavior. And we get similar patterns actually when we look at animal communication. So here again, the x-axis is time, and then each bar represents one frog call. We don't have the high volume frequency here because there's only so many frogs in a pond. But we do still see these kind of clusters of signals happening really quickly. So you can think of this like the spikes in Bitcoin trading, except for in this case, it's just a high density of signals in a short period of time. And the reason that we get these similar patterns is because these are both self-exciting point processes. And what I mean by that is, well, I guess I'm going to turn to earthquakes to explain it because it's a little bit more intuitive. So if you think of earthquakes, once you have at any given location, you have some background probability or rate that there will be an earthquake. And that might be higher in some areas, near a fault, and lower other places, but there's some background rate. And once you have one earthquake, though, then you have a higher probability of more earthquakes in very short time after it, and that's why you get aftershocks. But over time, as it gets longer and longer away from the original earthquake, the probability of another earthquake goes back towards that background rate. So that's what I mean by a self-exciting point process. And so I think we can use the class of models that would be used for modeling stock market trading or for earthquakes to actually understand these behavioral motivations for why animals are emitting signals. So I'm going to walk you through the general structure of the model and then an example applying it to birdsong and frog calls to show how you can use it for animal communication. So the general class of the models is you have your observation of a signal y at time t, and it's distributed as a Poisson process. But the key difference here is that it's a variable rate. So lambda is changing over time. So at each time t, you have a different probability of a signal occurring. And we can break the overall singing rate into its component parts. And so that's this background rate mu, which would be like if we were just running a regular Poisson process. And then the conditional intensity at time t, and that's the additional probability that you'll get another signal based on the history of events leading up till time t. And so this is the really fun part of the Hawks model, is how you actually figure out how to incorporate the history of the process. And so the conditional intensity is based on the self-excitement parameter, which essentially is if there is a signal and an individual can remember that signal, how likely is it to then respond, and how much does that increase the probability response? But of course, you also have to remember the history of signals, and so we have a memory kernel. And here I've set it with an exponential decay function. So we have this decay rate, and that essentially means that the longer ago an event was, the less likely it is to actually lead to a response, because you can't remember the complete history of signals, kind of like with longer time since an earthquake, you're not going to get as many aftershocks. And then you have the complete history of the event leading up till time t, but of course, the longer ago it was with this decay rate function, it won't be as important. So that's the general format of the self-exciting point process models. And now I'm going to apply it to a couple of example data sets. So since you would normally want to, or not normally want to, but normally people would run these types of models with just a Poisson model, we did both a Poisson model and a Hawks model to understand whether or not they were both able to fit the data and also see how well they performed. And then we used two different data sets. So we have one data set that is bullfrogs calling at a single pond for one breeding season, and then a second data set that is ovenbirds, which are these guys, in several different forest fragments across a few years. And so now I'm going to walk you through essentially the model performance and how well the models performed on the different data sets. I'm going to show you several graphs that all look like this. So I'm going to orient you first. So on the y-axis here, you have the density. So this is essentially just a posterior predictive check of how well the models were performing. And then the x-axis is the model estimates minus the observed calls from the data set. This dashed line here is 0. So if the models were perfectly predicting the observed data, they would fall right on the 0 line. Anything to the right of the line means the model is overestimating the number of signals, and to the left, the model is underestimating. Okay, so here are the results for the Poisson model with the frog data set. And you can see it does kind of center over 0, so that's good that the models are fairly well predicting the observed data set, but there's quite a bit of spread across the different recordings. So we have, I think it's 9 or 10 different recordings from the single pond. And when we fit the exact same data set to the Hawks model, again, it's centered over 0, and it's a little bit more, I guess, towards the center is the best way to describe it, so it's not as spread out. And so both models are doing a fairly decent job of actually describing the data and being able to predict the original. When we do the same thing for the ovenbird data set, again, exact same structure for the graph. You can see that it's slightly over predicting the number of songs, but doing fairly well, and it is fairly close to 0, where it would be perfectly predicting the observed data. And again, we get a little bit more tendency towards 0 with the Hawks model, but both models are doing pretty well in terms of their predictive ability. And so the main reason then to actually use the Hawks model as opposed to a Poisson model, which of course has way fewer parameters, is because we can start to understand those underlying behavioral motivations that I talked about before. So here we have the overall singing rate, which you can get from either the Poisson or the Hawkes model, because it's just the complete like overall lambda for the process. And we can look at it in terms of environmental factors. So here we have the time in the breeding season, which we might think for birds, maybe singing goes down later in the breeding season, but that could be for several different reasons. So for example, it could be because there's changes in this unprompted rate of singing. So maybe birds have already established a territory and attracted a mate, and that's why they're no longer singing. But it could also be changes in how they're responding to neighbors. So, maybe early in the breeding season, they're unfamiliar with their neighbors and more likely to respond. And towards the end of the breeding season, they're, familiar with their neighbors' songs and not as responsive. But we can't actually get any of this information if we only fit the Poisson process. And so that's where the real advantage of the Hawkes process models comes in, is because we can now break it down into the component parts. And so we can separate the unprompted rate of singing, which is that background rate mu from the self-exciting point process model. And we can see that does seem to be going down with time in the breeding season, whereas the responsive part, so the conditional intensity within that self-exciting point process model, is staying fairly consistent. And I should say this is really preliminary data. I haven't actually run tests on this yet because we're still working on entering data, but it seems to be a general pattern there. And that's just like the beauty of the Hawkes process models, is you can actually look at factors that might affect these. So not just time and breeding season, but we can look at habitat quality and things like that. So to wrap up, I just want to leave you with the overall structure of the model here, and emphasize that it's just it's a different way of thinking about acoustic signals in terms of breaking them down into the different component parts. And the real beauty of the Hawkes process models is that you don't actually need any additional information. You don't need to go out and get observations to figure out if an individual is paired or not. You just need the time series of calls. So with that, I'd be happy to take any questions.